Section 11.4, Series and their notations. So in this section, we're going to use summation notation. We'll find the sum of the first n terms of an arithmetic sequence and geometric sequence. We'll also find the sum of an infinite geometric sequence if it exists, and we'll look at an example of an application of series called annuities. So here's an example. Elmo decides to start exercising. He begins on January 1st by walking around the block 1 time. Each week, he circles the block 2 additional times. So 2 questions. How many times will he circle the block at the end of the year, in other words, in week 52? And how many times will he have circled the block altogether during the year? So let's take a look at Elmo's exercise regimen. So in week 1, when he starts, and let's just call that the first term of our list, he circles the block 1 time. And in week 2, he's going to do it 2 more times. He'll circle 3 times. In week 3, he'll do 2 more. That's 5 times. In week 4, he'll do 2 more. That's 7 times. And so the first question asks us, what would the 52nd term of this list be, of this sequence be? Well, we can answer that question because we know about arithmetic sequences. So a sub n is equal to a sub 1 plus n minus 1 times the common difference. So I can answer this question that by the end of the year, he will circle the block 1 plus 51 times 2, which is the common difference. So we can add that up, 51 times 2 plus 1. At the end of the year, he'll be walking around the block 103 times. But the second question asks something slightly different. How many times will he have circled the block altogether during the year? In that case, we want to take week 1 and add week 2, add week 3, add week 4, and keep on adding until we finally reach the end of the year. And so what would that be equal to? When we take the terms in a sequence and add them together, this is an example of what's called a series. So when you want to add together the terms in a sequence, we formed a series. And this is an example of an arithmetic series because we had an arithmetic sequence. Now, an arithmetic series can have what we call partial sums. So for example, when we write s sub 2, what that means is take the first 2 terms and add them together. So we could say s sub 2 would be equal to 1 plus 3, or in other words, 4. So the second partial sum is equal to 4. Let's do another one. S sub 4. That would be take the sum of the first 4 terms of the sequence. So in this case, it would be 1 plus 3 plus 5 plus 7, or in other words, 15. And so to answer question B, what we're wondering is what would S sub 52 be? What would the sum of the first 52 terms of this sequence be? And so that's what we're going to learn how to do. Okay, before we can do that, we have to investigate something called summation notation. So summation notation looks like this. This is the symbol for summation. It's a Greek letter sigma, and it's like a Greek S. And S stands for sum. So that's the symbol for summation notation. Now, when you have a summation notation, there will be something called the index of summation, often the letter K, but we can use any letter we want, a lower limit, which tells us where to start, and then an upper limit, which tells us where to stop. So for example, in this case about Elmo, we would like to add up starting from term number 1 to term number 52. And, oh, did we write one? Oh, we didn't write it. A formula for the arithmetic sequence would be a sub 1 plus n minus 1 times the common difference, which is 2. So if we said I want to add up the terms of this arithmetic sequence, that was what we were trying to figure out in the previous problem. So we're going to practice reading and evaluating summation notation, and that then will lead up to how do you find the sum of an arithmetic series. Okay, so let's evaluate this sum. The lower limit of summation is 1, and the upper limit is 4. And here is how we're going to generate every term. So first thing we're going to do is we're going to fill in 1 for k, and we're going to get a 3. We're going to fill in 2 for k. We're going to get a 6. When k equals 3, we're going to get 9. When k equals 4, we're going to get 12. This symbol means we should add them up, and the reason we stopped was because our upper limit of summation said stop when you substituted 4 in for k. And so we would add these up, and we would get 30. Here's another example. Let's evaluate this summation. Now notice this one starts with k equal to 3. So when k is equal to 3, that term is equal to 3 squared, or 9. When k is equal to 4, the next term would be 16. When k is equal to 5, the next one would be 25. And now we're going to stop because 5 is the upper limit of summation. And we're going to add these together, and we're going to get 50. So now here's one for you to try. Pay attention to where the lower limit of summation is and when you should stop, and then add up your terms. Okay, let's check your work. So when k is equal to 2, we have k plus 1, 3. When k is equal to 3, we have 3 plus 1, 4. When k is equal to 4, we have 4 plus 1, 5. And finally, when k is equal to 5, we have 5 plus 1, 6. We add these together because it's a summation, and we have a sum of 18.